No, I've been waiting for this one to show up. Hello everyone, it's October 23rd. Alright, let's see what we have today. Flip equivalent binary tree. I might have done this before. Ooh, maybe not. Wait a second, I think I have. Not only do I have, I feel like I've done this in an interview. Maybe, because it looks very familiar. You just flip it, right? Yeah, I think I've done it before. All right, I mean, do it again. For binary tree, we can define a flip operation as follows. Choose any node and then swap the left and the right child subtree. Okay. A binary tree is flip equivalent. Oh, this is not to flip it. This is to check if they're flip equivalent. Now that is different. If and only if we can make x equal to y after some number of flip operation. All right, so this is very different. I don't think I've done this before. So not only it's not a full flip, it's just to check if you can go from one tree to the other by flipping it. And a flip is to swap the left and right child. So we're given the roots of two binary trees. Return true if the two trees are flip equivalent or false otherwise. So are they flip equivalent? The number of nodes in each tree is 100. Each tree will have unique node values from 0 to 99. Okie dokie. So how do you propose we do this? Well, 100, so we have a lot of leeway on what method we use. And yeah, we can check on every node, right? We can check on every node and we will use, okay, basically it's this. Can we use flip to go from one tree to the other? So we use, let's say the right tree, root 2, okay? We use the right. All right, you use the second tree as the base, so we want to flip into that. And we have this tree, right? So the root is the same, and I check the left and check the right. If the left and right are the same, then we just keep moving on. If they are not the same, then we will swap. Not swap, we'll flip. Basically, we just say instead of going left to left, I'll go to the right. I'll go to the left. Right? And if the two are not the same, now if you swap it, it cannot make it work. Then we return, oh, okay. If we do it this way, this actually does not feel very hard. Okay, let's do this. I think we can probably get this in one run. I feel like this is not a hard problem. This is a true medium because I immediately found some solution or some resemblance of solution right away. Okay, so Boolean, we have two. Oh, that's perfect. Right, that's perfect. Okay, so of course we can say if because we check left and right, so there will not be empty. Okay, if root 1 equal to null and root 2 equal to null, okay, then we return true. If root 1 is not equal to null and root 2 is not equal to null, and then we need to handle this case. Otherwise, return false. Okay. Now, how do we handle this case? Then we say if root 1 dot val is not equal to root 2 dot val, we return false. They have to be equal as we are at the parent. Now we look in the left and right, okay? Then we can say, they have to match, right? They have to match. So how can we make it? All right, let's say root 1 dot left and root 2 dot, yeah, there are, if you're making a check here, right? If you're making a check here, maybe we can, because we just need to swap, right? After we swap, we're fine. And okay, so how do we handle swap? So I have root 1 left and then root 1 right. Oh, there'll be a lot of if. I'm not sure if I really want to do that. Well, if there is no, yeah, let's just, I mean, we have 4 children and then we just exhaust all the combinations. Okay, it'll be like this. If root 1 dot left is equal to null, right, and root 1 dot right equal to null, and root 2, oh, I feel, is there a better way than this? I feel like there is a better way than this. I mean, essentially, you can swap them, right? Oh, I have an idea. So instead of doing this, we just do one way and then we do the other way, right? It will be like this. So we can say return flip. Yeah, that's actually good. Equiv, right? Flip equiv, right? We return this. So we're gonna say root 1 dot left, root 2 dot left. This is not flip. Ooh, okay, hold on. So we're gonna do this. Wait, I don't like this. Okay, let's do it this way. Right, we'll say this and flip equiv root 1 dot right and root 2 dot right. So this is not flip, right? This is not flip. So we'll take or we take this flip equiv root 1 dot left and root 2 dot right and flip equiv root 1 dot right root 2 dot left. All right, let's see. So this basically, we don't go through any check, we just flip them, right? So we say the one is we'll do, yeah, and then we'll short circuit, so which is good. And okay, let's give this a shot. Yeah, performance wise, I think this one I don't have to worry about performance. Yep, I think this is right. Yeah, I was earlier thinking, oh, how do we write all the if and else to handle this? Well, the trick is you don't have to, right? For each pair of root 1 and root 2, first consider the edge cases, right? The edge cases such as one is null and the other is not null, etc. Then when both are not null and their values are the same, we can proceed, right? We can proceed with 2 possibilities. Flip, continue of the next round of check, right? Round of check. Flip or not flip. we will take the OR of the two outcome. All right, here comes the difficult part. What is the time complexity of this? So each time we will, actually I don't know. I do not know. I think the worst case is the two trees are exactly the same and they are full, complete binary trees. And you have to check every single possibilities, right? You have to check every single possibilities. So we'll check no flip, and every time we'll check flip. Actually, I'm not quite sure. I'm not quite sure about the complexity here. You can say at every step, you can do one way or you can do the other way. Every step you can do one way, you can do the other way. So you can say 2 to the n. The worst case can be 2 to the n. That's 2 to the 100. That's a lot. That is a lot. Actually, I'm not now I'm not sure if it's gonna pass. I feel like this is my timeout. Would it time out? I mean, if the two are exactly the same. No, it will not time out. It will not, because the values are unique. So a flip would definitely cause it. So if that's the case, right, since it's unique, so there's only one way, right? There's only one way down. You don't have another way. Yeah, and since they're unique, there is only one way down. You either flip it or you don't flip it, right? If you don't flip it, that will be your arrow out. So, and then we basically go through every single one. So I'll call it ON. I'll actually call it ON. And since each value is unique, there is only one checks will return true. Right? One of the checks will return true. So the runtime, so the time complexity should be ON. That's what I think. All right, let's run this and let's check one more time. I run it. Yep. I was worried about it, but turns out there is nothing to worry. Good. Oof. That's good. Oof. All right, I'm pretty sure this one shall be the official solution. Yep, exactly. What? What in the world? Oh, why would somebody do that? Canonical form. All no values have the same pattern values in both trees. What is this canonical form? Oh, you traverse it. Find canonical form. Oh, swap subtree so that left is non-empty. I see. Oh, can do that. Okay, that's that. Now we have a choice. You can either do one of these. Okay, why do we do this? Because there's some solutions that you want to know. Wait, how did you do this? Oh, it's a copy and paste. I do not know how to solve this. All right. How about this? Why we do this? Shortest palindrome? Because there's some, I think it's dear me, KMP. Oh, I am using KMP. I am using KMP. Rolling hash. Manaches. Oh, we are trying to go through Manaches. Yeah, I think we solved this using KM. Oh my god. If you ask me to do it again, I don't even think I can do it. I remember it took a long time dealing with this. Okay. All right, I think this is the one we failed the last time. Two integers n and k. Return the kth lexically smallest integer. Wow. Wow. Yep, it's a very simple looking problem, but damn, it's hard. I think I had some ideas, but they don't work. Okay, I kind of remember. Yeah, but at times, all right, all right. I have a little bit of context. All right, let's take a look. Prefix tree. This is what we're looking for. You need to find the kth smallest number in lexicographical order within a range 1 to n. At first, this might seem like a simple sorting problem. We could list all the numbers, sort them, yes. But it would become big, right? Instead of generating the sorting, we can treat numbers as trees, where each node represents a number and its children represent numbers with the same prefix. Okay. Structuring numbers this way allows us to find the kth smallest more efficiently. For example, the number 1 has children 1, 0 all the way to 1, 9, 2. Okay. This gives us a prefix tree-like structure where each node corresponds to a number and branches out to other numbers by appending digits. If we traverse this tree in lexicographical order, it's as if we are listing all numbers in their proper order. I agree. So if we traverse this tree using, I don't know, what's that called? Pre-order, the left root right. Wait. No, it's left. It's children first and then parent. Children first and then parent. No, because 1 goes first. 1, 1, 0, 1, 0, 0, right? And then, no, it's root, left, right. All right, you go root, left, right, right, right. Okay, yeah. So we just need to produce this tree. But are you going to, what's k? You can go all the, you can just iterate through them. Because I remember that my idea previously was to count so we can arrive at a k faster. Apparently they have an even better idea. I don't even see k, that's the thing. There's no k. It's just log n squared. Alright, we begin by selecting the smallest lexical as 1. Since we've already counted 1 as the first number, subtract 1 from k. Next, we calculate how many numbers exist in the subtree rooted at current by defining a helper function called steps. Okay, which counts the numbers between two prefixes, current and a current plus 1. It calculates numbers at each level, expanding the prefix as we go deeper. We know the kth number is not in the subtree if the number of steps or numbers under current is smaller than or equal to k. Under these circumstances, we skip to the next sibling. Agrees. And subtract the number of steps from k because we skipped. Okay. On the other hand, if the number of steps is larger than k, we know the kth number is in the subtree rooted at current. In that case, we move down one level by multiplying current by 10, effectively moving to the next digit in the lexicographical tree. We also decrease k by 1 because we've taken one step deeper. Repeat this process until k becomes 0, at which point we've found the kth number. Okay, so how do we handle this function, count steps? Because you have to deal with n, right? You have to deal with n. Let's keep reading. Initialize current to 1. And I think I understand this part. What I don't understand is this function. Okay, let's take a look at this function. Count steps, initialize steps 0 to keep track of the count of numbers in the range. While prefix 1 is less than or equal to n, add the number of integers between prefix 1 and prefix 2 to steps using steps plus equal to math.minimum n plus 1 and prefix 2 minus prefix 1. Huh? Wait a second. Add the number of integers between prefix 1 and prefix 2. What is this prefix 2? Oh, that's prefix 2. But this function is generic, right? So you can have a prefix, we can have another prefix. And you're telling me that the steps is prefix 2 minus prefix 1. This ensures the count does not exceed n by capping this if prefix 2 is larger than. Multiply both by 10 so they move to the next level. So we want to find out, let's say, the difference between 1 and 2. How many is in them? So we do 1 and 2, and we have one number between them, which is just one number. Okay, one number. And then we move on. 10 and 20. Ten numbers, 10, 11, 12, all the way to 19. 10 numbers, go to here. Okay. But really, how many numbers exist between prefix 1 and prefix 2? While prefix 1 is smaller than n. Really? That's it? Prefix 2 times, so you just go down. Hold on, from one to the other, right? From one to two. It's basically everything on one side. So 1 to 10, right? 1 to 10, 10 to 19, and then 100, 19, because it's like this: 1, 10, 11, 12, 19. 10, it can be 100, 101, all the way to I don't know, because this has to be 110, right? So 109. Everything's split into 10. Everything's split into 10. So we're saying is from a 10 to 20. Not really 10 to 20. We just, the difference is going to be 20 minus 10 is these much. The next level is 200. So it's all of this. It's 100, because this is going to be 109 all the way to 199. Does make sense. We just keep the prefix as the next one. And every time we go to the same level, then we can count, and it's eventually prefix 1 is going to hit n, right? It has to be smaller equal to n. So if I count here, and then that's why it's a min n plus 1 and prefix 2. N plus 1, because you don't reach there. So it's capped. It's capped at that level. So you're still at the same level, but you don't reach there. You reach someplace here, and then and then times 10 and become wow, this is great. Right? This is great. And then we start from 1. We count between 1 and 2. So if it's good, so we start from 2. We do 2, 3. Right? If it's too big, then we go down to 20 and 30. Between 20 and 30. And then will be 20 and 30, 21 and 31. Is that how we go? Yeah, if it's small, then we move on. If we have too many, right now we have too many. So if we have too many, then too many numbers. So it's not all the way there, right? So we get a level lower. I get a level lower, so from 20. We can count from 20 to 21. And 21 to 22. 21. I hope that is how it's going. Okay, let's see. K larger than 0. Step. We find this. If step is smaller than K, current plus K minus. Yes. If step is larger than K, current move down. Yes. Oh. Wow. Oh, this is a great problem. I think you can. It's a tough problem, right? But it has a very simple solution, which is if we don't do 10 to the 9th, let's say we do, I don't know, 10,000, right? 10,000, and the candidate can write a function, just, turn everything into string and then sort it, and then, just go with it. Yeah. So, but the next level is, okay, so instead of 10,000, we do like a billion, 10 billion, whatever number you can think of. Then what do you do? Right? What do you do? Then you can introduce this, what's it called? Prefix tree. Right? You introduce the prefix tree. And then try to see if you can, but this is hard. I think this is pretty hard. You need to really get into, even if you get into the right mindset, implementation is tough. It's a tough problem. All right, I've read the tutorial. I think the next step is to implement it. We'll do it tomorrow or maybe some other time. All right, I will see you guys.